Hello and welcome to polarity and molecules discussion. Today we'll look at, okay, is a molecule polar and how does that work with intermolecular forces? Going to cover a bunch of material here. So with that said, it's just an introduction into some of the topics that cannot replace some practice of your workbook, and you need to get other questions you have answered. All right, so first things, what forces hold molecules or ions together? It's important to distinguish the fact that if we have an ionic compound, that this is held together by what we call coulombic attraction, which is just positives and negatives attracting. But of course, the fundamentals of how that sets up is a little different for each particular bonding type. Ionic is just going to be a cation strictly bound to another anion, and another anion, another cation, and in a crystalline bulk crystal. So, whereas a molecule has a few different portions here. If we were to draw a molecule out, let's just say X covalently bound to Y. In this case, we have a unique subset of intermolecular attractions between molecules. Now, we refer to these as intermolecular attractions. This is going to determine whether this thing is a solid, a liquid, a gas. It will determine its vapor pressure, and it will determine its solubility. So that will probably be discussed on a later video on the results of, or the consequences of being polar. But in the end, what we're looking for here is, do we have a dipole moment? That means on my molecule someplace, do I have a positive region and a negative region? Now this molecule could be very simple, or it could be a very complicated molecule where we only have a positive and a negative here, or you could have a positive region, a negative region here, and a positive region here. These molecules vary in length, shape, size, function, but in this sense, do we have a dipole moment means, do we have one area negative, one area positive? Okay. How does a dipole moment differ with bond type? Again, that goes back to the fact that ion compounds set up in crystalline structures as opposed to covalent compounds produce molecules. So at some point for a molecule, because it doesn't have a specific cation or anion, it has to have a region where some reason, the electrons are being dragged across the atom. Now, protons are in the center of the nucleus. They cannot change. Let's just say we have two molecules here that are covalently bound to each other. Then the electrons, which normally would be sitting around the outside, and you might think they're relatively evenly spread across the atom, so we would not necessarily have an area of negative or an area of positive. It's relatively evenly balanced out. That is sometimes the case, and if that were the case, we would call this particular molecule pure covalent. Another name for that would be non-polar. Okay. Now, for some reason, okay, some atoms, again, the protons cannot move. The electrons, okay, they're sharing between here. Single bond means they're sharing. But for some reason, the electrons spend more time on one side of the atom as they do to the other, which just makes it proportionally negative on this side and proportionally positive on this. And now again, it's not like an entire charge of negative ones over here. So we'll see quite often a little symbol that looks like this, and they'll write it relatively small, means partial charge negative, partial charge positive. You cannot just write -1 this thing, or -2. It just isn't the case. It's not that big of a charge. Unlike an ion, which could be -1 and +2, which that is the actual charge. Anyways, so at some point, these partial charges will then attract to another one of these guys. It doesn't have to be the same item, but quite often it is. if this is the partial negative and partial positive, then we're going to have a Coulombic attraction of this positive to this negative and vice versa. So the rest of this PowerPoint really is going to be how do we know if this molecule has partial charges? And that is where we are next. We call this thing a polar bond. Polar bond is one where we're sharing, but we're not sharing equally. We have a nucleus, and for some reason electrons are being dragged to one side versus the other, and there's a little symbol. This just kind of shows why it is. Now, we're sharing, but we're not sharing equally. This is usually done or conceived as being responsible for a fact that's called electronegativity. Okay. Now that means we have a highly electronegative atom, and electrons are being dragged from one side of the highly electronegative atom versus the other one. So this is defined as an atom's attraction for electrons in a bond. Now, electronegativity, just so you know, increases to the upper right-hand corner. They all have values, but the big ones are nitrogen, oxygen, and fluorine. So in order to have an unequal sharing, we need to have a nitrogen, an oxygen, and or a fluorine, one of these three, bound to some other element. This is going to cause what we call an electronegativity difference. Now, Linus Pauling made up the electronegativity scale and gave it some meaning. Where he said if you were to look at an actual atom molecule, you could look at the actual, let's say two different chemicals here, okay? Water molecule, you could assign the electronegativity for this atom, assign the electronegativity of this atom. This is electronegativity is 3.5, this is 2.1, and you literally could subtract these values and to get what we call electronegativity difference. I'll just call ED, electronegativity difference. And versus this guy has an electronegativity and this guy has an electronegativity, so it is 4.0 and 4.0. Subtract those two values and your electronegativity difference equals 0. This guy has a dipole moment equaling 0, whereas this one looks like it is what, 1.4. So you'll find an electronegativity difference scale that says, okay, if your electronegativity is really different, then you're going to be ionic. So that would be like taking something, the smallest electronegativity would be francium, the largest would be fluorine. You put those two together, the largest difference, or really any non-metal versus a metal, the difference is going to be big enough to qualify as ionic. And then if they're close but not exactly the same, we call it polar covalent. And if it is very similar, we call it pure covalent. And means being shared almost equally. Okay, so we're going to use this difference of electronegativity to determine whether a molecule has what's called a polar bond. And you could go through, and if given the opportunity, you could actually get the individual electronegativities, subtract them, and apply them to this particular scale. And each book might have a slightly different value for what we think the electronegativity difference needs to be ionic, or what it needs to be polar covalent, meaning you have a polar bond. Okay, this is what we're looking for in this case. Polar substance that's molecular, or if we're just simply a nonpolar compound here. You can do that. On the AP test, that's never available, and really all you need to do is this. do we have one of my big three highly electronegative atoms bound to some other substance? Okay. Now, normally, well, there's a couple options here. So, how could this happen? Well, we could have, I'm going to label this page hydrogen bonding. Okay. Now, in this case, we'd have one of our big three, nitrogen, oxygen, or fluorine, bound specifically to a hydrogen. So we could have ammonia. Okay. We could have water. Pretty common would be an alcohol. All right. So we have this situation where we have one of our highly electronegative atoms bound to some other element. Now, I could have a sulfur trioxide. Okay. In this case, and that the bonding, there are some double bonds in there, and I'm not going to put those in, but essentially we do have an asymmetrical molecule where we have a highly electronegative atom drawing to one that's not. Okay, specifically we would call this a dipole, which means simply we have a molecule that has a region of negative and a region of positive, and it will attract to another molecule that has a region of negative and a region of positive, and they simply attract two dipoles. A specific type of dipole is hydrogen bonding. It appears to be a little bit stronger, so it's more common in biological situations, so it dominates the landscape here. And water would be your very common example of this. Of course, these are covalent bonds right here. They are not the hydrogen bond, very important. The hydrogen bond is what occurs between that molecule and another water molecule, or anything that happens to have a dipole moment. That is right there. Now, when we want to know whether something actually is polar, I follow this particular chart. Is my molecule polar? So do I have a polar bond? That's my first question. Yes or no? If the answer is no, I don't have a polar bond, then that means I am working with a substance that is a pure covalent. There is no difference of electronegativity. So the question is, do I have a nitrogen, an oxygen, or fluorine? If the answer is yes, well then it has to be bound to some other element. Okay. If this situation, difference of electronegativity is occurring, no, well then that means our molecule, the electrons and the protons are evenly spread throughout the molecule, evenly shared, and you are non-polar. If there's yes, well then there's the opportunity for something else to happen. We can have a polar bond where electrons are being dragged to one side versus the other and still not be polar, and that has to do with what's called symmetry. Okay, meaning that we have the opportunity for an atom to have symmetry, yes, and not to have symmetry, no. If we have symmetry, means that we have, let's say, a highly electronegative atom bound to some other atom, let's say, well, let's just put X and Y here, okay, but it's balanced in all directions. So there is, even though we have one atom which might be highly electronegative, be pulling negative, 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 we still don't have the situation we're looking for, which is one area is negative, one area is positive. We don't have that lopsided region. We need a situation where is it symmetrical? No. Where we have, let's say, cyanide, where we have nitrogen bound, triply bond in this case, to a carbon, where one region is lopsided, all electrons are being pulled to this side, and this side becomes positive. So at this point, symmetry, or the actual, what we call molecular geometry, okay, molecular geometry is entirely important, okay. We'll spend a little bit of time here looking at the molecular geometry.
All right, so as we continue here, our goal was to say, okay, if a molecule has a polar bond, then there's an opportunity for the electrons to be dragged from one side of the atom to the other, creating a lopsidedness of charge. Nitrogen, oxygen, fluorine, one of these guys bound to some other substance. This is going to cause an electronegativity difference. If we don't have this, then it's very difficult for electrons to get dragged from one side of the atom to the other. There is one more option, but we have yet to discuss that in this point. So either way, if the answer is no, then we are nonpolar. If the answer is yes, then we have to take one more step, which is involving symmetry. As mentioned in part 1 of the video, we have to consider this idea of symmetry only because it's possible that we have a polar bond and have it draw electrons to one side, to another side, to another side, and to another side, and have it actually be quite symmetrical, and we never have one area of negative or one area of positive, which is kind of what we're looking for. So we need a lopsided molecule which will draw electrons to one side, partial charge negative, partial charge positive. Anyways, so in this case, symmetry, how does it work? Okay, there are essentially 5 different shapes. I'm going to start a new page here. Okay. We call them the center atom. Okay, I'll put this right here. Okay, and things that exit the central atom, let's say Y and Y, to atom Y, atom X, atom Y, a shared pair. Okay, we call these anything that comes off of that atom an electron domain. That is not necessarily my term. It's a term I've seen used in POGL activities and various texts. So we could have an atom coming off this, or I could have an unbonded pair of electrons coming off this. Again, we're referring to this as an electron domain. I could have 4 things coming off the center atom. Okay, I have seen as many as 6 things coming off the center. So either way, that would be 6 electron domains. Now, all these things are negative. As far as the electron cloud is negative, this guy has its own electron clouds around the outside. It's negative. These guys, all the outer edges are negative because they all have the electron clouds. So in a sense, they're all repelling against each other. And negative via Coulomb, in this case repulsions, they push away from each other. We call this the valence electron shell repulsion theory, sometimes referred to as VSEPR. What that says is that the VSEPR theory is that no matter how many electron domains we have, they're going to push to get maximum room. So if I have 2 things bound, I'll just use X for this shape. I have 2 things, electron clouds here, electron clouds here. They're not going to get any closer to each other than 180 degrees. We call this shape linear. If I have 2 items, okay, and therefore now I have a center, X, let's go Y, Y, and Y, then again, electron cloud domain, electron cloud domain, and we are pushing now away from each other in all different directions. Now, this is a 2-dimensional sheet of paper you're looking at here, so it's only possible for me to draw out this in 2 dimensions, even though it's actually in 3. So keep that in mind. I'm just going to go for the base shapes right now. This has 3 electron domains, and therefore we call it trigonal planar. Okay. Then we have the 4 electron domains, And now's where, again, this isn't a flat plane, so if you drew it sideways, we have X, we have Y going here, we have this Y, again, still flat here. We have another Y stretching back here, again, still flat. Now we're moving into things that are not flat anymore. Sort of a, it's called four things in the center, it's called tetrahedral, okay? Y, Y, and then going straight back, Y, and then one goes straight up is Y, and follows sort of this triangular shape, or it goes back. No matter how you rotate this thing, it's still going to look exactly the same, even though drawings are sometimes hard to show that. Okay? We call this, with 4 electron domains, tetrahedral. Okay? 5 shapes, 5 things. All the center is called trigonal bipyramidal. So we have, in this case, an equator. X is in the center. We call this the equator region. I'm going to just, and then one going on the axial and one going down. I could put the Y's here. It just doesn't matter. Just assume that they're on the end. Again, I will show this as being part of an equator. Okay, and this is going up and down. Your bond angles, in this case, would be 120 degrees, because you have 3 things around 360. So this is always evenly spaced. And then we have 90 degrees here. The previous one, this is looking at 109 degrees, and this guy is 120. You should be looking for maximum room here. And then if we have 6 things off the center, we're looking at a thing called octahedral. Another name for this is square bipyramidal. Okay. 4 things off the center, and I'll draw this as being sort of in a plane. X is in the center, and let's go Y around the outside, and then in this case going straight up for Y and straight down for Y. Forms an octahedral shape. I'm just going to draw this to try and show you this is all in one flat plane. Now it's interesting that that's all in one flat plane, and this course goes this way. Alright, and if we drew all these together, we'd have what's an 8-sided object. Okay. Either way, if you rotate this thing, it would simply fall to the same exact shape right here. No matter how you tip it, it always looks the same. And we're looking at an 8-sided object. Alright, it's hard to draw. Anyways, so 8 domains, like that, up and down. Octahedral. In this case, everything is 90 degrees. The more you play around with these 6 basic shapes, the better off you can feel more comfortable with them. So a quick recap, we have simply linear. We have on a flat plane, trigonal planar. We have a little pyramid looking guy called tetrahedral. We have trigonal bipyramidal. And we have final one, square planar. Okay. Now, as we go through and look at some of these shapes, you'll find that sometimes we have bonded pairs and sometimes we have unbonded pairs. So, for example, we could have, and I'm going to go through each shape individually, starting with the Again, hybridization is another way of saying how this thing kind of works, how it all goes together. If I have three things coming off my center atom, this is called an sp2 hybridization. This got dropped from the AP exam as of 2014. I still kind of show people, and all it means that all the bonds overlap, orbital shapes. It forms this shape here. If we have just this location, this full geometry, we're talking trigonal planar. As we remove items, we get unbonded pairs. And I'll show the unbonded pairs as a pair, as a slot like this. Again, this does not show up in the family picture, and we end up with this shape. This is called bent. We're looking at 120 degrees. Still follows the same exact geometry, just that part of it's missing. Unbonded pair. Unbonded pairs take up more room, so technically the angle here is a little less than 120, maybe 117. Okay? For our purposes, you should just know that's a little less, or approximately 120. If I were to go sp3 hybridization, that's four things off the center. It's going to follow the tetrahedral formation, which is like this. Now again, as things get removed, we get a few different shapes. We get, in this case, a pair missing. I'll draw it like that. This is called trigonal pyramidal. Okay, you should see that both of these shapes, okay, are our first shapes where this thing is asymmetrical. This is asymmetrical. Everything at this point has been purely symmetrical. All my base shapes are symmetrical. If I were to remove another one, it would look like this. Okay, all I have left is my bent and unbonded pairs. And that is, in fact, the name. It is called bent. Well, again, the unbonded pairs take a slightly up more room. My angle here is less than 109, and these guys here are a little bit less than 109. In fact, this is going to be looking at about 105, and this is looking at around 107. If I were to look at the 5, give me a second. Okay, 5 things come out of the center. We call it sp3d hybridization. This is going to be called standard shape, 3 things off the center, 1 up, 1 down. Again, this is symmetrical. All right. If I were to remove one of my bonded pairs and create an unbonded pair, which is going to make it asymmetrical, then it looks like this. Up, down. Keep my equators and lose one of my equators. We call this seesaw. Lose another one. Up, down. We call this T-shaped. Again, asymmetrical. If we lose 3 of them, all the equators get lost. This one happens to be symmetrical, and its name is linear. If I were to take 6 things off a center, we'd call it sp3d2 hybridization, and there we go. Again, this is called octahedral, or square bipyramidal, and it is symmetrical. As I start lopping off things, doesn't matter which one because each one of them is the same. I'm going to keep for visuals reasons, we'll take the bottom one off. And this one is asymmetrical. And my final one would be all my equators, missing a top one, missing a bottom one. Let me call it square planar. Okay, it's flat and it is symmetrical. Now, whenever we look at a molecule to use these particular items, we just take time in class to look over them. Understand there's a lot of stuff here. If you're in general chemistry or honors chemistry, you could be able to use a note card to try and keep some of this stuff straight. But the more you use it, the more you'll know it. I would say if you have a real problem looking at some of these things, really you'd want to focus on just some of the smaller ones. I would say SP2, SP3, this would probably, from this point up, would encompass 90% of what we're going to see. Okay? And don't worry about some of the other ones if that is an issue for you. Otherwise, keep looking through it. Now, let's go ahead and let's use some of this. Okay? I want to be able to use my chart to say, okay, am I polar? By looking at my two steps. Okay? Do I have polar bonds? PB, polar bonds. Am I symmetrical? Question mark. You gotta be able to run through this with your eyes closed. Let's take it, for example, water. Draw out the Lewis structure. Oxygen, hydrogen, hydrogen, unbonded pair, unbonded pair. All right, so a few things you might want to note about this one. Okay, do I have polar bonds? So do I have a nitrogen, oxygen, fluorine? So polar bonds, the answer is yes. Oxygen is highly electronegative, bound to some other atom. Okay. Am I symmetrical? The answer is no. So right now, am I polar? Yes. If I had to draw out this thing, it would look like this. Partial positive charge, partial positive charge, partial negative charge. What type of intermolecular forces would be involved? This is called hydrogen bonding. Okay. Shape of this thing, because of the unbonded pairs here, its shape, the molecular geometry is bent. Okay. Its bond angle right there is a little less than 109 because of the unbonded pairs here, so it is approximately 105 degrees. That's an example how you'd run that through. Of course, in class we would do a bunch of these. Thank you very much.